All right, welcome back. In this video, I'm going to be talking to you about matrix inverses. So first, let's define a matrix inverse. So we'll say that a inverse matrix, A inverse, is going to be the type of matrix that if we multiply it with A, we get back the identity matrix, which I defined for you in the matrix arithmetic video. And now I did already show you how to find the inverse of a 2 by 2 matrix, and so I'll just be reminding you that and showing you how to find the inverse for a larger square matrix. Now, before I begin, I do need to remind you that, the inverse matrix will not always exist for every square matrix. There will be situations where the inverse doesn't exist, and then, moving forward, we'll look to categorize it. And just in case you forgot, the identity matrix, the n by n identity matrix, is the type of matrix that it's like multiplying by 1. It doesn't do anything when you multiply it by a matrix, and it's the thing that's got, ones down the main diagonal and zeros elsewhere. Zeros everywhere else and ones down the main diagonal. So maybe I'll start with the 2. So if we want to take the inverse of a 2 by 2 matrix, there's something that we can just remember that's really quick. So if M is the matrix ABCD, then M inverse is going to be equal to 1 over AD minus BC times the matrix where we switch A and D and we make B and C negative. Whoops. So that's negative C and negative B. Okay. Now, in class, I proved that this was the inverse using the technique that I'm about to show you. But, I just didn't find it to be the best use of time and certainly not the best use of your time right now watching this video. So that's the type of thing that if you wanted to verify this formula, you could go and you could use the row reduction technique I'm about to show you to verify. So for a quick example, here's A. I want you to think about finding A inverse in terms of X. So you can kind of just follow along with me here. All right, so that's how we're just going to apply the formula. It's 1 over AD minus BC. On the original times what happens when we swap A and D and make B and C. Okay, so this is in terms of X, this is what it's going to be. And then kind of the question that I was getting towards is when would the inverse not exist, right? What value of X makes M inverse not exist, or A inverse in this case, not exist? Okay, and if you look at it, it's like, okay, what could go wrong? It's the division there, and we could be dividing by 0. So if X was negative 2, then we would have a serious problem. Now, you might notice that if X was negative 2, then we would have this proportionality between our columns or between our rows. And that's, something that we're going to talk more about at great length, as we move forward in the course. Now let's start by finding the inverse of a larger matrix, like a 3 by 3, a 4 by 4, a 5 by 5, an n by n with n bigger than 2. And let's go back to kind of the definition of a matrix inverse. It's the matrix A inverse where if I multiply it by A, I get the identity. Now, in the last video, we saw that if we were trying to solve a vector matrix equation, like, suppose we were interested in solving AX equals B, we saw that what we could do to solve this matrix equation was we could row reduce A augmented with B, and, if we were lucky, and we had like a unique solution for X, then we could row reduce this all the way down to something kind of like the identity augmented with X. And I'm not going to actually write that, but we're going towards reduced row echelon form, heading towards identity augmented with X, right? Okay. If there was a unique solution, we could go all the way down to identity augmented with X, or maybe with some rows and zeros at the bottom if we had a tall matrix situation. But over here, what I'm proposing is that we will just augment A with the identity matrix and row reduce. But like, why would that be okay? So going back to the equation in blue, AX equals B. Well, couldn't I, if I was just, kind of restricting myself to just the first column of the identity matrix, right? If I wanted to solve for that, solve for a matrix, or for a vector that would get me to the first column of the identity, I could row reduce A augmented with the first column of the identity, and then that would give me a column vector X that I could, multiply it by, and then I could multiply A by on the left, and then get the first column. Okay. But then what I'm also kind of proposing is that the way that matrix multiplication works is that if we instead took X and we kind of added on a second column to it, and it became a matrix X, well, that would become A times X1, and then to the right of it, A times X2, if X2 was like the second column of X, matrix X. Okay? So what I'm saying is that if we were to solve, AX equals I1, AX, maybe I'll call it AX1, AX2 equals I2, all the way down to AXN equals IN, then we would have all of the columns of the matrix we would need to multiply A by to get identity matrix, okay? Which would be all the columns of the inverse. Now, hold on, go check right now. Yeah, I thought that, for some reason I thought that in the transforms video I had talked about solving for a matrix, and we were only talking about solving for a vector. Okay, so here, kind of lost myself, but what we're going to do is we're just going to, instead of doing these one at a time, we're going to augment A with all the columns of the identity matrix, because the row reduction steps we would take to reduce A would be exactly the same if I did, like I was saying, all of these different ones in gray. If I did them kind of in series, it would be a lot of row reduction. I'd be doing the same steps over and over again. And moreover, like whatever is happening on the right side of the vertical bar on our row reduction is, well, it's kind of restricted to that column. And so us adding more columns onto the right side isn't going to really the additional columns aren't going to impact the first, is what I'm saying. So what we're going to do is we're going to augment A with I, row reduce A augmented with I, and get I augmented with A inverse, right? Provided that A inverse exists. If it doesn't exist, then we won't be able to get I on the left side. If A inverse exists. All right. Now let me just show you kind of the mechanics of doing one of these. So here you go. Here's a 3x3 matrix. Find its inverse. Okay. And, I was going to say, I'm sure there is some nice formula out there, but it's not going to be as easy for us to remember as the one for 2x2. And I think, we don't just need to just find the inverse for 3x3 quickly like that. So I'm going to augment with the identity matrix, and I'm going to row reduce. All right. So my first step is going to be, I'm going to take row 2 and subtract 2 copies of row 1, and I'm going to drop that in row 2. I will also take row 3, I will subtract row 1, and that will give me now I think my next step is going to be to use this 1 right here to clear out the second column. So that'll be, I'll take row 3 and I'll add 2 row 2s, and then I'll take row 1 and I'll subtract 2 row 2s. Okay, so that will give me And now it looks like it might be a good idea for me to multiply my third row by -1, and so that'll become a +5, a -2, and a -1. All right, now I'm going to use this one to clear out the third column, and so I'm going to take row 2 and add 3 of row 3. And then I'm going to also take row 1 and subtract 9 of row 3. And that will give me probably something I'm not going to be able to fit right over here. So I'm going to just write it here. And then we'll see, oh look, I've got the identity matrix on the left, so that must mean I'm done, and I've got B inverse on the right. And so I will conclude that B inverse is the matrix -40, 13, 5, 16, -5, -2, and 9, -3, -1. And I'll let you check that on your own if you want to just make sure that's the inverse. You can multiply that by B and make sure you got back the identity matrix. All right, now the last thing I need to show you about is just some properties of inverses. And, you know, in the textbook, this is listed as kind of a 4-part theorem, and these are all related. But the first one I think you would find to be like self-evident is that the inverse of the inverse is just A. Okay? So I'm not going to go through and talk too much about that because I think that's pretty obvious. The ones that we want to know about are, how do we take the inverse of a product, right? Because we know that matrix multiplication does not commute. It doesn't work so nicely. What I'm going to tell you is that this is, if we multiply the inverses, the inverse of the product is the product of the inverses, but we have to reverse the order. Okay? And so why would that be the case? Let me just kind of give you a kind of sketch of a proof over here. Well, if the inverse of AB is B inverse A inverse, then we had better be able to take B inverse A inverse and multiply it by AB and get the identity, right? So what I'm going to do is I'm going to say, okay, matrix multiplication does not commute, but it does associate. So I'm going to say that this is equal to, I'm still in my shot, B inverse times A inverse A multiplied by B. A inverse A is the identity matrix, so, you know, if I had B inverse times the identity times B, I guess I could apply the associativity here and say that, well, the identity times B is just going to be B. Like that. And then B inverse B is going to be the identity. Okay? So that means if these two things here multiplied together to equal the identity, and I suppose, I didn't do this in class, I didn't think about this, I would need to do it the other way to make sure it works both ways. So AB times B inverse A inverse. Well, it's going to work the same way, right? I'm going to apply the associativity. I'm going to, some of our previous discussion leaking down. So A times B, B inverse times A inverse. Same thing, I'm going to, B and B inverse is going to make an identity. I'm going to be left with A times A inverse. That's going to be the identity. So I've showed that the first times the second is the identity. I've showed that the second times the first is the identity. That means that the first and the second are inverses of each other. Okay, how do we take the inverse of the transpose? Okay, that's the transpose of the inverse. Okay. I would probably let you verify that yourself. And then the last one is that if we have taken a matrix and multiplied it by a constant and then we want to inverse it, that'll be 1 over k, 1 over that constant times the inverse matrix. Okay. So, and this one is also kind of easy to see why it would need to work, because, you know, you need to be able to multiply k times a times some other matrix to get the identity matrix, and 1 of the identity matrix, not k of the identity matrix, so it makes sense that we need to divide by k as well. Okay, so those are some matrix inverse properties that you'll need for some of the problems on the homework. But I think the big message here is if you want to find the inverse of a large square matrix, augment it with the identity matrix, row reduce it until you get the identity on the left side, and then what you get on the right side would be the inverse matrix.